Okay, students, we're on chapter 12 now. Hopefully you did well on your benchmark. Um, we will be talking about mixtures this chapter. So we're moving from gases back to mixtures. Hopefully you guys did pretty well in the last unit, and I'm hoping you guys are learning your lesson about getting your homework done correctly. I've had some complaints, but if you don't answer the questions correctly, then you're not going to get credit for them. Alright, chapter 12. Section 1, Types of Mixtures. Here we're going to talk about 3 specific types of mixtures. Guys, these are physical combinations. We can always pull these back apart. You can probably do evaporation to separate the components. You could do distillation, which, guys, that's basically a fancy way of boiling 2 things apart. You can do filtration. And we'll talk about this one later. You can do chromatography. That's where you use electricity to separate the particles. Now, here we're going to talk about 3 different ones: suspensions, colloids, and solutions. There are differences in these 3 things, and in order to identify them, you've got to know the differences. So pay attention, stop when you need to, and make sure you look back at this for your homework. I'm going to answer pretty much every single question on your homework in this video. The first one we're going to talk about are suspensions. Suspensions have particles that are over 1,000 nanometers in size. Now, guys, that doesn't mean a lot to you, but just think these have big particles in them. They have big particles that will settle out. Okay, suspensions will settle out. This is one of the indicators as to which one it is. Now, when they settle, that's because the particles are too big to stay up in the liquid. And these have what we call heterogeneous appearance. You can see the heavier particles, generally because they're at the bottom, and you can always separate it by filtration. Think about orange juice sitting in your refrigerator. When you get it out, unless you got the no pulp, when you get it out, you've got to shake it up so that the pulp at the bottom goes all the way throughout it, and you don't end up with just the watery part at the top. Also, muddy water or sand in water, anything like that would be a suspension because the bigger particles will fall out over time. Okay, moving on from suspensions are colloids. This is where your particles are kind of medium-sized. They're between 1 and 1,000 nanometers. You can see these particles under microscopes, but you can't see them with the naked eye. These particles will not settle out and cannot be separated by filtration. You can tell there's something there, though. They don't always look the same throughout, and they exhibit something called the Tyndall effect. Look at all these examples down here. You can see that generally stuff that has like a gel-like nature is going to be considered a colloid. The particles are a little bit bigger, so they don't end up settling. You don't get to see each part of it. And just take a good look at these examples. Here are some pictures to go along with your colloids. If you look at all of these examples down here, you can see they're slightly thicker. Now, it's not like the homogenized milk or anything, and it's not like the sand in the water where it'll easily settle out and you can separate it quickly. These take a little more work to separate. Fog, hairspray, clouds, smoke, particulates, these are all gases, these are all dissolved in gases. So here you have liquid aerosols where liquids, let me try that again, where liquids are dissolved in a gas. Here you have solids dissolved in a gas. That'd be like smoke or the exhaust out of your car. Then we can look at gases dissolved in a liquid. Gases dissolved in a liquid. You can look at a liquid dissolved in a liquid, which is called an emulsion. That one's pretty big. You can find a lot of stuff that are emulsions at home. Blood, interesting enough, is a solid a solid dissolved in a liquid. Think about your platelets and your red blood cells dissolved within. Then you've got foam. I know this one's kind of weird. That's a gas dissolved in a solid. That's why it's squishy. Jello or jelly is a liquid dissolved in a solid, and a solid dissolved in a solid. This is called cranberry glass. I've never seen this one before, but apparently it's a thing. Okay? These are a bunch of examples, but do not put this down on your homework. When I ask for examples of solutions, make sure you're giving me solutions, not colloids. That'll come here in a few minutes. Now, how can you tell if it's a colloid instead of a solution? Because sometimes those look a lot alike. You can tell if it's a suspension because you just have to imagine it settling out. Now, this is the kicker. The Tyndall effect is when the mixture itself scatters light. So if I run light through a milk and water or a milky solution, it's going to scatter light. You're going to see that light. It won't go all the way through the liquid. It'll scatter and the light will be pushed out in all directions. Okay? Think about fog. When you guys are driving in fog, are you supposed to use your high beams or your low beams? Hoping you said low beams. And that's because if you turn them on high, that light's going to reflect right back to you. It's going to blind you. If it exhibits the Tyndall effect, this is always a colloid. If it doesn't scatter light, it can't be a colloid. It's probably either solution or a suspension. Here's the one we use most often, solutions. Now, why do they look homogeneous? Well, that's because the particles are less than 1 nanometer in size. These are tiny little particles mixed into a liquid generally. It could be a solid, but the particles embedded or mixed throughout are very, very small. Now, these will not settle out. They cannot be separated by filtration, and they do not exhibit the Tyndall effect, okay? I would say that these tend to be clear or the same color throughout, but sometimes they aren't, okay? You just need to keep in mind, you have very small parts. They look the same throughout. Therefore, they're homogeneous. The particles will not settle, and it does not scatter light. Okay, so let's talk about solutions. They have two parts. You have the part being dissolved, called the solute. That's the solid or the liquid or whatever you're pouring into the solvent, which is the dissolving medium, or the part that does the dissolving. Now, they can come in all shapes and sizes, so let's look at some examples down here at the bottom. You can have a gas dissolved in a gas. That'd be like air. All of those gases are mixed within each other, and that's what we breathe in on everyday basis. You can have some CO2, you can have some oxygen, some nitrogen. All that stuff is in the air at any given time. You can also have a gas dissolved in a liquid, like CO2 in water, or carbonation in water, which gives us soda. You can have a liquid dissolved in a liquid, like alcohol in water, or you can have any other compound that's a liquid dissolved in water, such as like iodine or anything like that. Bromine specifically would be a good one. Then you have solids dissolved in liquid, like sugar and water. This is one of the most common for us, or salt water. Whoops, salt water. Or you could have Kool-Aid. It's anything that you put a solid into a liquid, mix it up, and the solid ends up dissolving. Or you could have a solid in a solid. Now, the big example for this one would be an alloy, such as brass, bronze, steel, all those things that we're used to talking about. 14 karat gold is also an alloy because it has some stuff in there that's not exactly gold. 24 karat gold is pure gold, so if you buy gold, buy 24 karat if you want it to be the real thing. Oh, here's the alloys that we talked about. This is always a solution of two metals. So it's all, well, most commonly it's a solid in a solid when it's cooled. Now, brass is made of copper and zinc dissolved within each other. Bronze is copper and tin dissolved within each other. And steel is iron with carbon put in there to make it a little stronger, to keep it from being as pliable. Now, these are always created to give more strength and to make them resistant to corrosion. Because as you guys know, copper can rust very badly. I'll show you guys when I come back, but if you leave a piece of copper out in the air, it will oxidize. The oxygen will act on the copper, and it'll start pulling the electrons away from the copper, and that's what gives it that green tint. Sometimes it'll look black. Okay? That's an alloy in a nutshell. This is the ones we were talking about before, aqueous solution. This is anything where the solvent is water, where whatever you're mixing in or dissolving is dissolved in water. Now, there are two classes to this. You either have electrolytes or non-electrolytes. Electrolytes, as you can read, are substances that dissolve in water to give a solution that conducts electricity. These break up into ions. So if it's an ionic solute, it's going to be an electrolyte, okay? So say it's NaCl dissolved in water. Well, when I put this in water, these are going to separate into their ions, okay? The positive will go toward the oxygen end of the water molecule, and here's your hydrogen end, which is positive. Remember, that's polar. So the positive part of the sodium will be attracted to the oxygen, while the chlorine will be attracted to those two hydrogens. And it pulls the bond apart. Now, when it does this, it conducts electricity because you have free-floating ions. Anytime you have free-floating ions in a solution, it will conduct electricity. Here's a visual of what I just showed you guys. The chloride ions, when they pull apart, you see how they're surrounded by the blue right there? They're attracted to those hydrogen ends, while the sodium is attracted to the oxygen ends. Now, look over here on the right, and I know this picture got cut off, but here you have sugar, or sucrose, I believe, and it does not conduct electricity because it doesn't break up into ions. It does dissolve, but it doesn't give you positive and negative ends. When you're looking at acetic acid, you get a weak signal there, weak current, because they partially break up. The acetic acid, the hydronium or the hydrogen will pop off, and you get a little bit of charge there because you're left with acetate. Here's your salt water, sodium chloride. Notice it's very bright because it breaks up and those ions can carry the electricity. We're going to talk about this a little bit more later in the year. And then hydrochloric acid, that's a very strong acid. It breaks down very readily, and you get chloride, and then you get hydrogen, which the hydrogen, which we call hydronium here, attracts all the oxygen, and the chlorines attract all the hydrogens. So that's why this is the brightest. Electrolytes are organized into three categories: acids, bases, salts. Acids always have a hydrogen attached to an anion. Bases always have OH attached, I don't know what I'm doing there, attached to a cation, and salts are cations attached to anions that come from the acids. Okay? Non-electrolytes do not conduct electricity because they do not form ions. It's not made of a metal plus a non-metal, or the hydrogen or hydroxide. So I just gave you a bunch more acids down here at the bottom to look over, but I got to keep going. Okay, for homework, you need to be doing homework set 12-1. You're going to do all. Everyone's going to do all. Make sure you answer the questions correctly because I don't want to hear any crying when you get the questions wrong. Okay? Good luck.